Good day, everyone. My name is Marcy Johnson. I'm the current president of the Statistics Former Students Network of Texas A&M University, and we're very fortunate today to have with us Dr. Cheng from the Department of Biostatistics and Comprehensive Cancer Center at St. Jude's Children's Research Hospital. Dr. Cheng is a member of this department at St. Jude's, and he collaborates with investigators in the hematologic malignancies program in academic departments for providing statistical expertise in study designs and data analyses for clinical trials, laboratory experiments, and publications in peer-reviewed journals. He received his PhD from A&M in statistics in 1993 under the advisory of the late Dr. Emmanuel Parson, and then became a postdoc fellow at Upjohn Laboratories before joining Johns Hopkins University as an assistant professor in 1995. In the year 2000, he joined St. Jude, where he continues to lead the statistical design and analyses in translational, clinical, and laboratory research of childhood leukemia. He's co-authored several high-impact publications in this area, and he's been a member of the Institute of Mathematical Statistics, the American Statistical Association, since 1994, and was also a recipient of the Team Science Award from the American Association for Cancer Research in 2009. Dr. Cheng is going to give us a presentation on nonparametric failure time analysis, thinking outside of the Cox-Regression box and genomic applications. Thank you, Dr. Cheng. You can take it away.
All right. Thank you so much, Marcy, for the splendid introduction. And I'm really honored to be invited by the Former Students Network. And so it actually made me to recall the good old days in the Blocker building. And I think we're still in the Blocker building now, I believe, right? At least a part of the department. And my office mate was Todd Ogden, and he's also my academic brother, actually. And I think maybe many of you actually know Todd. And I at least know about him, and he's now a professor of biostat at Columbia University. So I'm going to talk about this is going to be a slightly technical talk today, and Marcy told me the audience will be mostly statisticians. I think it's going to be okay. And so I'm going to talk about a work that's published a few years ago. But there's still a lot of room for both method theory and applications in this area, I believe. I'll outline a few of those toward the end of my talk. And so, well, to begin with, just some acknowledgements, grants, and collaborators, etc. So let me start with this motivating example. As you may know, I work with in childhood leukemia, and one of the major questions we have in this area is that what is the risk of relapse after chemotherapy? And so this is an example from a so-called genome-wide association study where we study the mutations, point mutations in genes, and see how the mutations may relate to the risk and time to relapse after chemotherapy. So in that study, we encountered we call it single nucleotide polymorphism or SNP in short. So for those people who, if you are not familiar with genomics or genetics, you can just think conceptually that I have a factor variable X that has 3 levels, 0, 1, and 2. They are ordinal. Basically, what they are counting is counting the letter B in the genotype, right? So in this particular data set for this particular SNP, this is a situation we have. So 70 kids with the so-called AA genotype or X being 0 relapsed. But there's no relapse in the other genotypes. No X being 1, no X being 2, not in these 2 levels. And there are some other events that we call a competing event. There's some other type of failures, not relapse failures. And then many others, I say censored here, meaning that these people are survival fine. We haven't observed any failure in these people. The vast majority is in. I can see the vast majority they have the AA genotype or X being 0. And what's striking here is that the other 2 levels of X, 1, 2, or AB or BB, they are quite rare. It's very infrequent relative to the AA genotype. So if you plot out the cumulative incidence function of relapse in these three levels, what you can see is simply this, right? All the relapses events, 70 of them are all in this level, X being 0. And for the other two levels of X, there's no event, right? So if we run a Cox regression, for example, this is what we get. If we test the regression coefficient on X, p-value is 1. The coefficient is very big, but the standard error is huge. And there is a warning from R. If you run it in R, it's basically saying there's a numerical problem. The likelihood ratio tests seem to be okay, normal, marginally significant at the 5% level. And if we run another another regression, which is the counterpart of Cox regression in the context of competing event, and what we get is a marvelous result, very significant effect of this mutation that's very protective. The p-value is 0, and the coefficient is huge and very small standard error from fine and gray regression. And if we pretend that X is not ordinal, you just pretend it's categorical. If we run so-called Gray's test, which is a counterpart of the log rank test, it's not significant at 5% level. And if you run another test, that's a rank-based test, published a few, some years, 15 years ago, 17 years ago, and it's not significant. So we're getting conflicting results here. And also potential numerical problem if you run Cox regression in R. So what triggered this? This triggered me to think about, okay, probably first off, we need more omnibus and more robust methods here to deal with this kind of data. Because there's also, given this situation, it'll be difficult to assess whether the proportional hazards or relative hazards assumptions are actually satisfied in this scenario. So that's why I think, okay, we probably need to be a more robust, more omnibus test for the association, ignoring or going beyond the relative hazard or proportional hazard assumptions, like upon which both Cox and fine-grained regression. That's a basic assumption for those type of models. We need to go beyond those assumptions. So that leads to this idea, what I call it the correlation profile test, or CPT for short. Right? So I'm going to just present the idea in the classical survival setting, just for sake of passing the main idea. But this approach actually works better in the setting of competing risk, where that's going to be the setting of my simulation study. I'll show you in a minute. So formally, so let's assume that I have a sensor time, T of C, that follows some distribution, F of C. And I have a time to event, I call it T sub E, that follows some distribution, F sub E. So censoring and failure, we assume that are independent. So the only thing that we can observe is, of course, the smaller one of the two, right? Y is the minimum of the two. And when we do know what type of event that is, whether it's a failure or it's a sensor, so we do observe this sensor indicator, which is the indicator of TE less than TC, right? So then now we have an explanatory variable, a factor variable X, assuming it follows some distribution F of X. And here, the type of X can be either continuous or ordinal. In the SNP case, that's ordinal or binary, or even binary. Right? So this is what the observable data we have on any individual, right? So it's the time to event or sensor Y, the sensor indicator delta, and the covariate X, right? So I'm going to define the event process as one jump point process. That is, this process is going to be some random function n of time, n of t, is simply the indicator that the time to failure or time to event is less than or equal to t for any non-negative t, right? So the hypothesis, the association hypothesis of interest in the genomics study is now can be formulated as this. So it basically says that this event point process n is independent of x. That's the null hypothesis. Versus the alternative that n is in some sense, I call it stochastically monotone in x. Because here x I'm assumed to be at least ordinal. For binary, 0 is less than 1. So that we take that order, right? So that we can define monotonicity. Right? So I'll make this clear in just a minute. So in order to reflect this kind of association, stochastic monotone, it turns out the correlation is actually pretty good indicator for the alternative hypotheses. So for that purpose, for that goal, I've defined what I call the correlation profile function, which is simply the correlation of this one-time jump process with the covariate x for any time, for any non-negative time, right? So these are the fundamental population quantities that I'm going to deal with. So what do I mean by stochastically monotone? So keep in mind, so I have a one jump point process. This is the hypothesis I want to test for the association test. And so by stochastically monotone, I mean that I say this process is stochastically increase in x, for example. So that means if for any pair of x values, x1 less than x2, the conditional distribution of the observation n of t given x2 is always stochastically greater than or equal to the conditional distribution of the jump process given x equals to 1. And that should hold for all time points. Right? So just to avoid some triviality, I also request that the stochastic, the strict stochastic order should hold for at least one pair of x1 and x2. So that's what I mean by stochastic monotone. So the goal now then is to devise a statistic to test this pair of hypotheses, right? I think do feel free to interrupt me if you have questions. Okay, so how do I construct the statistic to test this kind of hypothesis, right? So conceptually, or we can visualize the survival course of each individual, like I said, as a jump process, the n of t, right? So this is an illustration of what we may see, or the visualization what we may see on each individual. Each line here represents an individual in my sample, right? For example, in the first individual, the covariate value is 2, and this individual failed at this time. So the process jumps to 1, from 0 to 1, and stay to 1 thereafter. And the second individual, the genotype or the factor variable is 0 level, and this individual stayed event-free until sensor time. Circle means sensor here. Same thing for the third individual. The factor level is 1. This individual stayed event-free, but it got censored early, right? And etc. So we can pictorially think or visualize that this is what we observe. This is our data, visualization of our data, right? With the aid of the one jump process n of t, right? So from here, it's not difficult to think that, okay, yeah, I can actually define a empirical version or sample version of the correlation profile function, which is simply the sample correlation of these processes NIT at any time t with the variable x, right? And in general, for continuous x, you may even replace x by the rank. That also works too, right? So we have this empirical, actually empirical version of the correlation profile function. But of course, t is continuous. It will be difficult to deal with for all possible times, right? So a particular way to construct the test statistic is that instead of looking at all the possible values of time, we strategically place some time nodes across the observation observed time period, and then aggregate these empirical or sample correlations across these time points to form the statistic, right? So these time knots should be placed strategically so that they will reflect well the distribution of failure times. So I'll talk about that in a minute. So this is the basic idea to construct the test statistic for the null independent hypothesis versus the alternative stochastic monotone hypothesis. Right? So more formally, so this is how the statistics can be constructed. So this is our data. These are the observables. Each individual is a three tuple, right? The observed time, either failure time or sensor time, the sensor indicator or the event indicator, and the covariate for n individuals. We'll have the IID vector, three-dimensional vectors like this, right? So then I can define the observed point process, one jump point process for each individual I. So you call it one if IT if the individual failed, and then the observed time is less than or equal to t, and the event is failure, right? Zero otherwise, that's still the patient is still at risk or not available if the patient is if the individual is censored, right, before the time t. So this is essentially the observable. These are the lines I showed just now here, right? So just write it out algebraically. So, and then we can define or compute the sample correlation at any time point t using all the available data at this time point, as long as the individual is still at risk or the individual failed before time t. These are full observations at the time t. So we can utilize that to compute the sample correlation. Or here, the n prime t is simply the number of non-missing observations at time t. Right? So we can compute the empirical correlation function this way. And then now the question is, how do we define the time knots to construct the statistic? So one possibility is that you can pick a small number, small integers, let's say 9, for the number of time knots, and then set each time knot to be the quantiles of the failure times. So this way, these time knots will reflect the actual time to failure distribution. So we want to make these knots as representative as possible, and so that this statistic will reflect the time to failure or time to death as much as possible. So then you define the statistic this way, right? So this is how formally the statistic is constructed. And it turns out, just like any statistics, you know, I mean, almost every statistic is asymptotically normal, and this is no exception here. And under two conditions, we have asymptotic normality. And the point of this theorem is that here, this actually hints how we actually constructed the test, right? So we know the asymptotic variance is tau square, but that variance is very complex. It's a function. It depends on the underlying distributions and number of knots, right? But at the same time, we know that it's of the classical rate, n to the negative 1 rate for the variance or rooting n rate, 1 over rooting n for the standard deviation. And so what this hints is that if we can get a good hand on this estimate, on the asymptotic standard deviation, somehow I will be able to derive a normal approximation test based on the SN statistic. And the question is how I go about it, given the complexity. I know it's on the right order, but analytically, this quantity is very complex. It depends on many unknown quantities. Okay. So, but the basic idea is that because this is the standard deviation under the null hypothesis, and then the basic idea then was that, okay, I can probably simulate the null hypothesis and get a good estimate of this asymptotic standard deviation under the null. And so it turns out that's doable. And the idea is that we can use permutation to create a estimator of the asymptotic standard deviation under the null hypothesis. So the idea is rather simple. So we just do plain old permutation. So what I do is that, let's say we do B round of permutations. So that I'll repeat this. So you randomly permute the data points of the factor variable xi. So you get a permuted sequence, and then you compute the CPT statistic, right, in each permutation round based on the permuted values of the covariance statistic. And so you do this B times, we got B of, in some sense, B observations of the test statistic, right? And under the null hypothesis. And after the permutation, the associations break, and that's a simulation of the null hypothesis. And then we'll simply just pretend this is our data under the null, and then just compute the sample standard deviation and use that sample standard deviation as an estimator of the asymptotic standard deviation under the null hypothesis. So then we know that this statistic should be close to standard normal distribution for large samples, and then the computation of the p-value becomes straightforward. This is a two-sided p-value, right? So this is how we go about to produce a significance test based on permutation and the large sample approximation to get the test, right? So if I do this, and of course, also the question here is how big the B is, but you can note that this is simply a moment, right? So we probably don't need a very big number of permutations. And it turns out, I'll show you in the simulation, in some scenarios, you can just use a few hundred permutations. That'll be good enough. Actually, I set B to 200 in all the scenarios I looked at. So back to the SNP example. So this is what I showed at the very beginning of the talk. So we see that we saw a problem with the Cox-Regression. We saw something looks good, but whether that's really true or not is questionable. And there's some conflicting results with these. And so where does CPT show us? And which this is a test that doesn't rely on any proportional hazards assumption, etc. And it shows that it's actually somewhere kind of in between these. And the test statistics is negative. That's basically reflecting this strong drop off here. But still, it didn't reach significance. It seems to me that's reasonable. And both these three tests actually seem to me a reasonable level of significance in the sense that the reason we didn't see any failure here in these rare groups is simply that the numbers there are too small. Maybe just by chance we don't really see any failure at all, because the failure here, the probability of failure is nonetheless quite low, right? Like in AA is 70 out of almost 600, right? Over 600 individuals. So it's a bit like 10%. So with these small numbers in these groups, if the true failure rate is also 10%, we hardly see. You may not be able to see any failures in these two groups. So it seems that in that, at least intuitively, there's really shouldn't be sufficient statistical evidence to demonstrate that these two groups are actually protective for relapse, right? So that's how it worked out for the SNP example. And so of course, to better understand whether this is good or bad, is this really a good test? We need to study further. So one possibility would be we use simulation studies, right? So this is a simulation model that mimics the SNP example I showed you just now, right? So I have an ordinal X takes the values 0, 1, 2, and the zero value is very frequent, has a 98% probability. the 1 and 2 values are rare. This is only 1.5%. This is 0.5% for value being 2, right? So I'm going to simulate the failure process in 2 steps. One step is that first off, I want to see whether there's a failure at all, right? Conditional on X, given X. So I set it to this probability. So this is just a Bernoulli random variable, conditional on X. So I set it to, this is the probability of having a jump in that one jump point process. And then given the jump, conditional that if I do see a jump, and I'll say the time to jump from 0 follows a log normal distribution. And the original normal mean is a scaling, with a scaling factor of the value of X. And the beta is a scalar and standard deviation 1. So that's the how the survival or the failure time process is generated. And then there's a universal independent time to sensor. I set it to exponential distribution with 0.2 rate. Okay. So here is how the simulation showed up. This is for the null case. I ran 1 million simulations. For the alternative cases, I ran 10,000 simulations. So for 2 samples, 700 and 1500, and I set the nominal significance level fairly high, not 0.05, but 0.005. This is because with the large scale genomic applications in mind, because in those cases, we typically require very high significance in order to reliably draw a conclusion on the gene mutation. Right. So for this process, from here, what you can see is that under the null hypothesis, this is what first of all I say, this SNP example, this kind of configuration is a rather quite difficult configuration for essentially all the methods to handle. And as you can see that at the nominal level 0.005, none of these methods actually hold the level well, right? And at the 700 level, if the sample size is 700, and probably CPT gives the level that's closest to the nominal level. This is a proportion of rejections or probability of rejections. So it's the closest, and fine-grained regression is really terrible in holding the nominal level for a relatively small sample size. And so are the other existing methods, right? And with even if CPT still doesn't hold the nominal level, but it generates the closest or the next to the closest, right, to the nominal level. So that's just the status of the art so far. But under the alternative hypothesis, however, what you can see is that when beta is non-zero, meaning that the time to failure condition on X also depends on X. In this scenario, this is some scenario that's a deviation from the proportional hazard or relative hazard assumption. In these scenarios, as you can see that once you have good enough sample size, CPT is quite more sensitive, quite more powerful than the other methods here. And simply for this kind of setup, 700 sample size of 700 is just not enough to detect the small deviations or test these weak alternatives, right? And when the effect size gets bigger, when the values of the parameters theta and beta gets bigger, as you can see that CPT at a modest sample size 700 actually outperforms the existing methods, right? But if the time to failure here is independent of X, it's only the probability of failure is dependent on X, but not the time to failure. If that is the scenario, we see in the small sample or model size samples, CPT is still competitive in terms of power. But in the large samples, like 1500, CPT, you see a little bit, some efficiency loss in CPT. Yeah. And I'll show you a little bit why that's the case. This is another scenario, which is exactly the opposite scenario of the SNP example. So here, the 0 level is rare instead of frequent, but the 1 and 2 levels are quite frequent, but 0 levels is rare. So that's exactly the opposite to the SNP example. And also in this rare group, there's a higher probability to fail, to death, or higher probability of death, right? So in this scenario, if you look at the same parameters, but actually we don't really need to go out to sample size of 1500. It turns out this is actually a favorable scenario for all the methods. And even with 200 sample size, we can get really reasonable powers. So you can see under the null, all methods hold the level quite well, except perhaps grays and in the fine gray regression in the small samples, right? So we see the same phenomenon. That is, if the failure probability is free of the covariate X, but the time to failure is dependent on X, CPT outperforms all these methods quite a bit. But on the other hand, if the failure probability depends on X, but not the time to failure, we see some efficiency loss in CPT compared to the other methods, right? So yeah, sometimes it can be like this can be substantial. So let me show you a little bit why that may be the case analytically. So you think about the simulation model. What we have here is that we have essentially a two-step way to generate that point process, right? So we have a Bernoulli random variable, right? So we assume that this Bernoulli random variable conditional on the covariate X follows some Bernoulli distribution pi of X, I call it. So again, I use T as the time to failure or time to death. That's the survival time. And the failure time process then is simply the product of T times the indicator that the failure time less than or equal to T, right? So the cumulative distribution function of T given the covariate X, and simple out, well, defined this way, that's simply the probability that T sub E less than or equal to T given that the death is 1 and the value of covariate, right? So that's that's conditional CDF of T of the failure time given X, right? So with this, you can write out the covariance of this point process at any time point T with the covariate X. So this is simply this integral. It involves pi, it involves the conditional CDF, right? So what you can see from here is that this covariance and consequently the correlation profile function, that's going to tend to be large in magnitude if the covariance of this product with X is high. It's large in magnitude, right? So as you can see, this integral is simply the covariance of pi of X times this conditional CDF with X, right? So it's not hard to recognize that pattern. So what that means is that if I see a high covariance between these two quantities, the CPT test is going to have power. It's going to be sensitive, right? Let's look at the first scenario. So if the failure indicator or the death indicator is independent of X, only the time to failure is dependent on X. What that's going to happen is that means that this pi of X is constant. So what that means is that CPT will be sensitive if this conditional CDF is highly correlated with the covariate X at every time point, right? So if you recall our simulation model, I said it this way. And when theta is 0, that means the failure probability is independent of x. And here, if I set beta to be positive, that means that only the time to failure is dependent on the covariate. And in this case, this is exactly the scenario where CPT has power. And this is also a scenario where there's a deviation from proportional hazards, right? So in this case, CPT obviously has a lot of power, both analytically, you can see from here, and from the simulation study we saw just now. And the next scenario is that the time to failure is independent of x, but only the probability of failure is dependent. So in that scenario, what we can do is we go through some algebra. What came up with is that the hazard function related to the conditional failure of x has this form, has this particular form. And if you look at this form, you can see that this is a very similar, very close to a form like this, which is exactly proportional hazards, except from the pi of x in the denominator, right? But in fact, actually, this lambda star is actually an upper bound of lambda 1, right? So what this says is that if the failure probability is dependent on x, but the time to failure is independent of x, we are in a scenario of almost proportional hazards. And if that's the case, of course, models designed for proportional hazards will be better because they are optimal for proportional hazards, right? So, and that's what we see in the simulation study as well, right? If theta is non-zero and beta is 0, we see some efficiency loss. That's because I'm comparing to an optimal test in this scenario. So that's why we see those the performance. We see those kind of performance pattern in the simulation studies, right? So that's so much for that. Let's go back to the. Let me show you a particular example. Let me see if I have enough. Yeah, let me show you a particular example. A actual application. So we want in this application, we investigated the germline SNPs on chromosome 9 and the risk of relapse in childhood leukemia. So I have in this study we have 929 subjects from 3 treatment protocols over the span about almost 25 years, I think, and it's comprising. There are 5 treatment groups or 5 treatment strata. So the endpoint or the phenotype or the response variable is time to relapse. And there is some competing risk, and this is not a major issue here I want to discuss. So from a assay platform, we can genotype about 22,000 SNPs on chromosome 9. For those, if you are not familiar with genomics, you can think about each SNP is an ordinal random variable, and they take values 0, 1, and 2. And in this study, I have 22,000 such ordinal variables, and I want to test for each of these variables their association with the risk of relapse. Right? Relapse response SNP is the explanatory variable. Right? So I ran a CPT test on each SNP or on each of these ordinal variables, factor variables, and for the hybrid permutation test, I used just 200 permutations, and turns out it worked quite well, right? So there's another details for this. By testing this many, making this many significant tests, there's a multiplicity issue, right? So in the large scale genomics and the measure of false, the level of false positive errors, or we use this called false discovery rate, and so I did have some assessment for the false discovery rate here. even if it's high, there are some interesting findings I'll show you in a minute, but this is a minor. And so this is a part of the results from the analysis. So each row here represents a variable or a SNP or a quote finding from the analysis. And I didn't say there's actually a stratified version of CPT. I don't have time to get into it. So I computed both stratified CPT and unstratified CPT and compared it with the two existing methods, the fine-grained regression and the stratified regress test, right? On top, these are the variables or the SNPs that's captured only by stratified CPT, but not by fine-grained or gray test. And down below here are the SNPs that are captured by fine-grained test, but not by stratified CPT, right? So one interesting finding I want to draw your attention to is this particular variable or factor. It's the mutation in the so-called ABL1 gene, and it's well known for ages that the ABL1 is a very important gene in the development of a rather very aggressive type of leukemia. And it turns out it's what's interesting here is that this is a new type of this is a SNP in ABL1, which is different from the known ABL1 mutations. And it turns out it also seems to have some role in affecting the relapse, the risk of relapse after chemo. And so let's put the biology aside. Let's look at a little bit more the statistics in this case. Is that here? I hope it's not too big, too small on your screen. And this is an old slide. I had it for talk before. If it blows up on the big screen on the wall, it looks great, but it's probably too small for you if you're using a laptop or your phone. So, but anyway, so there are these here. Each row is a strata. Like I said, there's a stratified version of CPT that's available. So each row is a treatment stratum here, and each column displays a particular type of information. And in the first column, that's the display of the cumulative incidence function of relapse for each genotype, or for each value of the X variable, 0, 1, or 2, right? And so I think the solid line 0, dash is 1, and dot is 2 for the X values. As you can see that there seems to be some weak effect of the mutation, meaning X being 1 or 2, right, in some of these strata, right? And in the middle, what I displayed here is that for each value of this random of this factor variable 0, 1, or 2, or the genotype AA, AB, and BB, the time to relapse as an event or time to censor, and the failed cases are solid, and the gray circles are the ones that are censored, right? So altogether we have more than 600 symbols here, right? And so each symbol corresponds to one individual, and you can see a little bit of weak trend here. That's that the mutation to B allele, meaning X being 1 or 2, it seems the proportion of failure is tend to be a little bit higher than in the AA group, because you can see that there are some number of failures, but the total number of individuals in this AA and AB and BB group, AB and BB groups are also small, like here. So in the BB group, this is like 1 out of 6 failed, relapsed, and they relapse very early, and similarly here. And so there's some relapse, but it's a relapse early, right? So it seems to be a weak trend that the mutation is detrimental for relapse, and that is also consistent with this third column. This column shows the empirical or the sample correlation profile function I showed you in the earlier slides, and you can see that at all the time points, the the correlation profile function is always positive, meaning that the failure time process, the n of t, is actually stochastically increasing, right? In the values of the factor variable, going from 0, 1, 2. So even if the effect is weak in each stratum, when you put them together, do a stratified CPT, and we get quite a significant result here. So that's what happened there in this particular example. So I think I'll leave the time for questions in the end if there is any. So a summary of the results. So seems to me from both the simulation study, the analytical insights, and the real data study. So we can say that the correlation test number one, it's completely nonparametric. It's just constructed from sample correlations, right? It ignores all the underlying distribution. As long as the correlation exists, it is meaningful. So it's computationally more robust because it's just a sample moments. We don't need to do any iteration to estimate, to maximize the likelihood, for example, right? And it's more omnibus from the simulation study you can see, or from the analytical heuristics you see, right? It covers the deviations from the proportional hazard or relative hazard model, right? It covers, that's a very big territory actually, right? Beyond proportional hazard. And so it's competitive with other nonparametric procedures such as Grace test, right? Especially when the data don't follow proportional hazards, right? And we do see some efficiency loss relative to these methods. But keep in mind, these methods are actually optimal under the proportional hazard or near proportional hazard condition. And so that's what I see, right? But there's actually seem to be quite a bit room for improvement. But first, I mentioned that the stratified version of CPT is available. I didn't have time to talk about that. And it's possible to actually extend this to beyond typical survival analysis or typical time to failure analysis. You can modify this statistic to handle recurrent event response or recurrent event phenotypes. And also there's another scenario I call informative censoring, or in some sense called informative dropout. And again, I don't have time to talk about the details, but the extension is rather straightforward, right? So what one need to do is actually just modify the coding of that observed point process. By properly modifying the coding at this 1 and at this NA, we can handle these recurrent events and the competing risk. But there is a complicating factor that is, if the risk or the time to a competing event also depends on the covariate X, that is a rather complex scenario, and it is not clear at this point what would be the best way to go for this CPT approach in testing the association or stochastic monotonicity of the point process with X. And this is actually, this dependency of the competing event on X raises some confounding issue here. And that's a pretty involved issue that I have no answer at this point. And another extension, what I would call it dynamic logistic regression. And it's that in certain applications, sometimes it may be desirable to know the main or perhaps even interaction effect of the factor of interest, I call it X here, after controlling or adjusting for other covariates, Z, right? And typically in the genomic studies, one sometimes, most of the times would want to adjust for the so-called population structure or population stratification. Everybody familiar with genomics will know that. And that will be another covariate Z, right? CPT cannot address this directly, right? For that, we have to resort to some sort of regression modeling. So what one can do is simply, we just replace the sample correlation at each time point by a generalized linear model. In this case, maybe logistic regression model here, right? And what we can do is that you can fit the logistic regression model at a grid of time points again. So that's the correlation profile idea. But now it's not a correlation anymore, but rather a logistic model, right? So you can fit it as a dense grid of time points, or maybe a sparse grid, like 9 points. I propose at the quantile locations, etc. Right? So and then you can just simply aggregate the coefficient estimates across the time points to form a test statistic, right? Or alternatively, if you want to form to estimate as a rather dense time point grid of time points, what you can even do is you can just stitch all these coefficient estimates together by a nonparametric regression, actually to produce a truly time varying function of the effect of X, right? In some time interval, right? There has to be an upper bound here for each particular data set for the estimate to be meaningful. So in this way, we can definitely extend the CPT idea actually to handle the situation when you have additional covariates that you need to adjust for, and at the same time we can show a time dependent effect of your covariate of interest X here. So how would that work? And specifically how we can make this work, and that's an open problem at this point, right? So I think that's pretty much all my technical presentation so far. And let me close to put in a plug. I'm in the Department of Biostatistics, and as you may heard, and at the St. Jude Children's Research Hospital, and also the St. Jude Comprehensive Cancer Center. And this is the SJCCC is the only NCI-funded cancer center that's solely dedicated to childhood cancers. And I want you guys to know that we are hiring, right? We are hiring in multiple categories and multiple levels. So we'll have faculty positions open, and at assistant level mostly, but we could adjust for higher level positions if we have great candidates. And we'll have postdoc positions open. We have staff statisticians open, and the staff statisticians position can be open rank as well. So the faculty research areas are largely genomics, multi-omics, clinical trial design, precision medicine, survival analysis, etc. And you heard genomics and survival analysis today. So if you know someone, students or associates or some who are looking for a career, academic career in a research institution, you just to let them know, and they can either contact me or contact the department chair or HR, however, and we have exciting positions open right now, right? Different type of positions. So that's all I have, and thank you for your time and interest. I think there's a few minutes left, and if you have questions, I'll take questions.
Dr. Cheng, there is a question in the chat from Dr. Kapoor. He says, thank you for this wonderful talk. The question is, how do we interpret the S question mark? Can it be used to quantify the strength of association?
That's a very good question. At this point, I would say probably not, or at least you need to be very cautious. And the test statistic I designed is just for detecting association. It's just like the chi-square test on a contingency table, right? Whether can you use the chi-square test to measure the effect? I would be careful about that. I personally don't think so. At least it's not a very good measure of effect size. And here, the test statistics solely designed to test the existence of monotonicity.
Sorry, Dr. Ogden has his hand raised.
Okay. Hey, Todd.
Hey, Chung. Great talk. I really appreciate that and learned a lot. I've got two questions. I hope it's okay to ask too. So the first one is you were looking at I was trying to think about this counting process, and you're looking at the correlation of a numeric random variable with the counting process. It would seem more natural to me to, instead of thinking about the counting process, to think about like the hazard function, or I guess the integrated hazard function or integrated log hazard function. I think that would just seem more natural to me as far as trying to work out the theory of that. But I wonder that might end up being exactly the same test. I'm not sure. And then my second question is a quick question. It seems like you treated X as being numerical throughout, although you said that it is actually ordinal in your applications. So I just wondered about that.
Yeah, okay. So your first question, I think I agree with you. If we go with the hazard rate function route, I might end up with the same thing. But it's also not very clear to me, if I go that route, how would I go beyond non-proportional hazard alternatives? No, it may be possible, but it's not clear to me at this point how that might be done. And here, this correlation approach is more along the line of accelerated failure time models instead of hazard regression models. And but of course, these two are related, like I showed you in the scenarios here, scenarios A and B, and depending on the nature of the underlying point process, right? And one may have advantage over the other, and vice versa. And yeah, and your next question, true. I mean, it turns out it's a little bit stretch of imagination that when you have a binary outcome, at each time point is a binary, right? And when you have a ordinal covariate, how the heck can the correlation work, right? And it turns out it works. Because I want to avoid modeling as much as possible. That's my first instinct to begin with. So if I avoid modeling, I will go the moment route, right? You use moments instead of. So that how this the sample correlation came about. I agree. It's kind of a stretch of imagination. How would this kind of Pearson's correlation, traditionally designed for continuous variables, how could it work on binary and ordinal variables? And it turns out it's not that bad, as you can see that it may be outperform the hazard rate regression, and it has a little bit efficiency loss in the optimal case for hazard regression. And also the good thing about it is that it will have a solid asymptotic behavior, which allows you to derive rather stable and accurate tests there.
Great. Thanks a lot, Chung. I appreciate it.
Thanks, Todd. Good to see you. It's been a long time. I don't know. Boy.
We have one more minute if anybody else has another question. Otherwise, I'm sorry.
Yeah, I'm sorry. Go ahead, Marcy.
And I was just going to thank you for your very interesting talk.
Thank you.
You raised some good questions, and we really appreciate you taking time out of your day to share with us some of your important research.
All right. Thanks again for the invitation, and thank you everybody for your interest and time.
Hello, I have another question. I'm sorry to interrupt you again. I wonder if you provide any statistical software to implement this algorithm.
I have an R code that implemented this S and the hybrid implementation test. If you want to get it, let me clean it up a little bit and send you. I didn't develop any package for this procedure, which is a good point. Maybe I should. Yeah.
Yeah, it would be nice if you are going to develop a R package, something like that in the future. That would be very helpful.
Yeah. Yes, that's a good point. Thank you.
Dr. Cheng, this is Brani. Thank you for giving us this nice talk. Excellent talk. You mentioned the positions available. We have graduating students and postdocs. If you can send information to Elaine about the position, I would be happy, and she would be happy to share this with students, graduating students and postdocs.
Oh, that's fantastic. Yeah, I will do. I'll send the contact person.
Thanks.
Yeah, to Elaine. Mm-hmm.
Excellent. Excellent. Well, thank you again so much. We appreciate your time today.
All right. Thank you, Marcy. Thank you all.